By now, I hope what you're seeing is that arithmetic in binary works pretty much exactly the same as it does in decimal, but the concept of place value has changed. And understanding binary arithmetic requires a solid understanding of what place value means. As we move from addition and subtraction to multiplication in this video and then division in the next, that theme will continue. As with addition and subtraction, let's revisit the method for multiplying two integers in base 10 and keep a careful eye on place value. So look at 263 times 13. Our school algorithm works like this. First, position the numbers vertically with the larger one on top, then proceed to multiply the first number by the ones digit in the second one. 3 times 3 is 9. 3 times 6 is 18, and just as in addition, that overflows the one-digit space allocated to it. So we write down an 8 and carry the 1. Now remember that it says 1, but it's actually a 10 because it's the tens digit of 18. And we're going up a place, and every place in base 10 is 10 times larger than the previous place. We carry the 1, then multiply 3 times 2 and add the 1, because that's what carrying is, it's just adding, to get 7. Now we move on to the tens digit in the second number, and we're going to store the result in a second row down below. Since this is the tens digit, not the ones digit, we shift everything in that second register over by 1 unit, because the result will start in the tens digit of the answer. In this case, the rest is easy because we're multiplying by 1. We just get 263. So then there's a final stage where we add both the lower rows, and just as before, we sometimes have to carry a digit when adding, and our final result is 3,419. Now, how would this work in binary? Let's start simple with 111 times 11. Let's just roll with this and try to follow the same rules as with base 10 multiplication. Well, 111 times 1 is just 111. Then in the second step, it's still 111 times 1, and that is still 111. But when we write it, we're shifting over a unit because we're multiplying by a higher place value, just as we were at this stage of the base 10 multiplication. So you can see that on one level, binary multiplication is shockingly easy because we're only ever multiplying by 1, which means just copy the number down, or by 0, which makes everything 0. So now we're just left with an addition problem, which we saw how to do 2 videos ago. Here we have 1 plus 0, although we don't write the 0, which is 1. Then 1 plus 1, which is 2, or 1, 0, so put down a 0 and carry the 1. Now we have 1 plus 1 plus 1, which is 3, or 1, 1. So put down 1 and carry the other 1. Then we have 1 plus 1, which is 1, 0. 1, 0, 1, 0, 1 is our result. And in base 10, that's 16 plus 4 plus 1, which is 21, which is good because the original numbers we multiplied are 7 and 3 in base 10. So in fact, the only thing really hard about binary multiplication is the binary addition that takes place at the end. Let's try a larger example, 11111 times 101. In base 10, that's 31 and 5, so the answer should be 155. Lining these up, we first multiply by 1 to get 11111. Then we shift once and multiply by 0. Of course, that just creates a string of zeros. Then we need to shift a second time since we're now 2 places higher. Multiply by 1 to get 11111. Now add these together. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. And this happens twice. 1 plus 1 is 0, carry a 1. And then finally 1, 0. That gives us 1001, 1011, which you can check is indeed 155. One more example will illustrate what happens when the addition at the end starts to stack up, quite literally. Look at 11111 times 111. That's 31 again, but this time we're multiplying by 7, so the answer should be 217. The multiplication steps are very simple, and here's where it leads. Now we have to add, but there's something new. We've never tried adding a stack of binary integers like this. In decimal, adding a stack of 3 or more integers works pretty much the same as adding just 2 integers together. Although when we do, these numbers can get quite large. Adding 2 integers together in base 10, we sometimes don't carry a 1, but for example, in this case, we'd have to carry a 2. We could handle adding a stack of binary integers in a couple of ways. We could just add the first 2 levels together and then add the result to the third level, and that would work, but it seems like more work than you need. So let's try to adapt the base 10 method of adding to binary. In the ones place, this is just 1 plus 2 zeros that we don't write, so we have a 1. In the twos place, we have 1 plus 1, which is 0, carry the 1. Now let's think. In the fours place, we have 1 plus 1 plus 1 plus 1. This is 4, and in binary, this is 1, 0, 0. What this means is that we have a 0 here, and we need to carry a 1 2 places up. It's like if we added a stack of decimal integers so high that the tens place added up to 106. We'd have to put down a 6 and carry the 1, but not to the next place up, but to the place after that, since in that case, the 1 is 100, not 10. So we'll carry that 1 to the 16s place, and we'll leave it until we get there. But next we need to add the 8s place. This is 1 plus 1 plus 1, which is 1, 1. So we're going to write a 1 and then carry the 1 up 1 place to the 16s place. In that 16th place, we now have 5 1s. That, of course, adds up to 5, and in binary, that is 1, 0, 1. So we'll write a 1 and carry that leftmost 1 up 2 places. Moving on to the 64th place, we have 1 plus 1, which is 0, carry the 1. So finally, we have in the 128th place, 1 plus 1 plus 1, which is 1, 1. The final result is 1101, 1001. Is it right? Well, let's convert to base 10, and we get 217, which is indeed what we were supposed to get. Phew, you've learned at least a couple of things in this video. First, the general process of multiplying in binary. And second, possibly more importantly, you've learned that place value is really what all of arithmetic hinges upon. If you can understand what all the digits of a number mean in terms of their place value, this unlocks all of arithmetic and also a real understanding of how a machine can do arithmetic. Next up, we're going to tackle our fourth and final arithmetic operation, division in binary.